Okay, this is CET236, and I'm just going to have a look and see how many people are online. So currently I just have a Van on the line. So Van, I'm going to wait a little bit and see if anybody else shows up. And the aim will be to, well, I'll go through these slides, these introductory slides, and we'll talk about the homework that's due, and talk about Thevenin and Norton equivalent circuits. Just going to check my Discord settings. Try that. Okay, give it another couple of minutes and then I'll start. Okay, good. Looks like we have August joining.
How are we doing, Professor?
Okay, not many people on, so I was just waiting for a couple more people to show up, if anybody's, and I'll start. So since you're here, let's start. So the topic this week is Thevenin and Norton equivalent circuits. But let's do my usual. I'll have a look at the where we are in the semester, and then I'll talk about the homework that's due, and run through any questions that people have about the homework, and
Okay.
then we'll do we'll watch the two videos about Thevenin and Norton equivalent circuits. Okay.
Sounds good.
Okay, so that's where we are. This is July 12th, and the aim is to talk about Thevenin and Norton theorems. Next week, we're going to shift gears a bit. We're going to basically start doing the whole course again, but this time, instead of the resistances being real valued, they're going to be complex valued, and instead of just having resistances in the circuit, or resistors in the circuit, we're going to have capacitors and inductors. And rather than talking about resistance, we're going to be talking about impedance, which is what you call the complex valued version. Everything we've talked about still holds. Ohm's law holds, mesh analysis holds, nodal analysis holds, superposition, maximum power, and Thevenin and Norton. But once you throw in capacitors and inductors, the impedances now, what used to be resistance, is complex valued. So once we've finished with tonight's topics, Thevenin and Norton, we will have done just about everything on the left-hand side. And then it's just a matter of, like I said, doing it all again, but this time for complex valued devices. So there's two homework assignments due tonight. There's the nodal analysis homework assignment, and there's the Lab 6 superposition assignment. I'm happy to go through either of those or both of those. Let's just have a look at next. So we don't, as you could see, we don't have much time left, right? After this week, we only have really 2 weeks of lectures. And then there's the final exam period after that. So what I've decided to do, the two assignments that are due tonight are due tonight. They will close tonight. But all other assessment, all the labs and the homework assignments are still due when I set them to be due. But you can hand them in at any stage up until July 26th. To encourage you to submit the assignments earlier than July 26th, if you do hand the assignments in on time, you will get a 5% bonus over and above anything else you get for the course. So it's possible to get 105% on the labs after starting the labs due next week, the labs and the homeworks. Sorry, was there a question?
Yeah, so the ones that are due tonight have to be done tonight, but then starting next week.
Starting next week, that's correct. That's correct. So the ones that have to be are due tonight still, and they're going to close tonight.
Okay.
But all other labs and homeworks I would still like you to try and get them done when they're due, but just because we're running up against the end of semester and there's lots of stuff due, I don't see there's any point in stressing people out too much about due times. It's still quite a bit of work to get done between now and the end of semester, but I'd rather you choose how you get it done rather than me forcing you into how you get it done.
And then if we do it before they're due, then we get extra credit?
That's correct. There's a bonus of 5%. If you hand it in before the due time, then what'll happen is if once you hand it in, it'll if you particularly for the labs, it'll tell you whether the lab is if the lab is late. If the lab is late, you just get graded as normal. If the lab isn't late, then you'll get the extra 5%.
Okay.
Okay. So yeah, so the that's what the big yellow box here is saying, right? So Homework 5, homework 6, I think it's homework 7 and 8 as well, maybe, and lab 7. They're all technically due. Well, they're scheduled for next week, but if you get them in by then, that's great. If not, you can still get them in and get full credit for them. You just won't get the bonus if you hand them in before the due dates. Okay. And just a reminder about the midterm. I have actually the numbers here are a little bit old. I think I've had another 2 students taken, so there should be 12 of 19 taken. I think at least another 2, maybe 3 students have booked. So I think there might still only be 4 students outstanding still to book. So if you haven't taken the midterm or haven't booked the midterm, please book the midterm. I've opened up some more slots next week. I'm technically on vacation this week, which is why I'm looking a little different on Discord. I'm using my laptop rather than the my desktop computer. Okay, so the things due this week are nodal analysis. What I thought I'd do, particularly for nodal analysis, is the last question is possibly something we haven't looked at or haven't looked at recently. So let's have a quick look at that in WebWork. I can figure out where WebWork got to. There it is. Okay, and let's copy that image, and I'll put that down here, and we'll talk about that. Let's see if I can find that on my iPad. There we go. Okay, so let's just undo that. Oops. Right, so this is the circuit out of question, I think it's question 6, is that right? In nodal analysis? Yeah, question 6 in nodal analysis. And it's a little different because it has that big triangular thing in the middle. That big triangular thing is either an op-amp or an operational amplifier. And in this course, we don't really deal with real operational amplifiers. What we're actually looking at are ideal operational amplifiers. And there's a few things about ideal op-amps that we need to know. That's not right. Right, so the first reason it's called an ideal rather than a real op-amp is the input currents, those the minus lead and the plus lead of an op-amp are the inputs, and the input currents I1 and I2 are 0. Okay, so what that means is even though they're inputs, they only look at the voltage that's there. They have no input current at all. What any operational amplifier, real or ideal, does is and this is a differential operational amplifier. Differential because one input is positive, the other input is negative. So this operational amplifier subtracts V1 from V2. Okay, so the output, V out, is given by K, some gained, times V2 minus V1. And for an ideal operational amplifier, the gain is infinite. Now, that may seem a little strange, and it sort of is, but what that means in terms of when we analyze the circuit is that V1 is always equal to V2. So let's have a look at this circuit now that we know those few things about an ideal operational amplifier. Okay, we're doing nodal analysis, right? So there's a node, and we've got current IS flowing into the node, and we could think about current IR1 also flowing into the node. Okay, and let's just quickly go back and have a look at the things we're given. Right, we're given that Vs is 2 volts, and we're allowed to use VA, VB, and VO as our variables. That's an O, not a 0. So in this case, we can see that we'll call it node A, right? We should be able to see that IS plus IR1 equals 0, right? That's just applying Kirchhoff's current law to the node where R1 and IS meet. There's no current flowing through here, right? Because of that equation there for the ideal op-amp, right? There's no current flowing into the op-amp. So the only currents flowing are the current from the current source and the current through R1. And then you should be able to see that IR1 is just equal to V out minus VA divided by R1. Now, last year I put together a video, so some of the stuff in the video is not correct. But let me just run the video, and that'll also give us some information about this particular sort of question. So, as I said, there is a problem with the op-amp nodal analysis question in WebWork, and it's to do with the way WebWork is set up. It's a new version of WebWork, and for some reason it doesn't like the way that particular problem was set up. So I'm just going to forget about that as far as a grade is concerned. So I'll just grade homework 5, nodal analysis, on the other questions, not on the last question with the op-amp. But I thought I'd show you how to do it anyway, right? And it should be pretty straightforward. And in my version, there was a 25 microamp IS, a 4 volt VS, and then the two resistors were both 18 kilo ohms. Okay? And the first question is about how many equations do I have? Well, I've got an unknown VA, an unknown VB, and an unknown V out, maybe also an unknown I out, but I can get that once I have V out. And so that means I need at least 3 equations. And there's going to be 2 KVL equations, and 1 KVL equation is here, right? That's just a voltage source connected between the reference node and node B, and then the other KVL equation is because of the ideal nature of the op-amp, the voltage difference between nodes A and B, between the inverting input and the non-inverting input of the op-amp, have to be 0. Okay, so there's the first KVL, right? 0 minus VB equals 4 volts, and that's okay. And then the KVL for the op-amp is just VA minus VB equals 0, or VA equals VB. And the KCL equation, we've got currents flowing into the node from the current source, and we've got current flowing out of the node through the resistor. Now, in what I just drew, I drew the current through R1 flowing the opposite way. That's okay. All you'll see different is a change in sign in the KCL equation for node A to the output, right? So there's the current into the node minus the current out of the node, right? The voltage across here is VA minus V out, and divided by 18 kilo ohms to get the current. And we can play around with that a little bit. And then solving the system, we already know VA is minus 4 volts, right? The positive side of the voltage source is connected to ground, so we're dropping 4 volts when we get to node B. So VB is minus 4, and then we know that VA, because of the ideal nature of the op-amp and the virtual earth idea, that the difference between the two inputs on the op-amp can't be anything other than 0. And so both of those are minus 4 volts, and then plugging both of those, or the VA value, into this equation here gets us what V out is. And then if we want to get what I out is, we know V out, we know R2, So we can just use V out minus 0 on R2 is minus 24.2 microamps. Okay, and that's the way to solve that question. I apologize for not getting it right as far as web work is concerned, but it is what it is. Okay, and I have seen that there's at least one student who hasn't been able to get, they've been putting the right answer into web work, but they haven't been getting the web work to accept it. So I suspect that problem may still be there. Let me just have a quick look at the nodal analysis question and see if I can look at problem 6. Right, and as I think I said, there's 2 KVLs and 1 KCL.
Yeah, I keep getting that my formula isn't linear.
Yeah, and I'm wondering that what I might do. This is Van, right? Yeah. What I might do is see if I can. I just want to try my version here, and if my version works, then what I might do is I might reset the random seed that chooses the numbers for everybody's question 6 and see whether that works. Otherwise, I'll do what I did last year and just say if you get anything, if the grade you'll get is only based on questions 1 through 5, and if you get any grade on question 6, that's just going to be a bonus. Okay. So let's have a look at this. KCL at A. So IS is 0. And that's 0.25. I think that's 25 microamps. Looks about right. And then the current flowing in. So I'll do it the way I wrote it up just now rather than what was in that video. That is now V out minus VA divided by R1, which is 18. And then because it's nodal analysis, let's just see if that gives me the same. Yes, it gives me the same problem. So it looks like there's an issue with that. It's going to be for everybody, and I don't know whether I'll be able to solve that shortly. So let's just say do as much of the nodal analysis questions as you can. If you want to try and get a little bit, you already know the answers to the first part. It looks like it's not going to accept. Well, you might be able to. What's the KVL at B? That just says that VB equals minus 4 volts, right? And then the op amp KVL, I think I said that's VA minus VB equals 0. So let's see if those two at least come out correctly. Yeah, so that should be able to give you the right answer. Right, so then VA and VB are both minus 4 volts. And I think I said that, was it 4.475? Is that right? And I'll show the correct answers for my version as well. Yeah, so they're all correct. Well, it says 4.45, but it looks like I got within the tolerance. And then the output current I out is just going to be that 4.4 475. Let's see if that's still on. I think my R2 was 18. And let's just see if that's right. It probably won't be close enough. No, it is close enough. Okay, so you should be able to get it all out. And if the only thing wrong with your answer is what it's saying about your formula isn't a linear one, I'll take that as correct because it's just WebWork being wrong.
It doesn't let me progress beyond that part of getting that the equations.
Oh, really? You can't open up... That's interesting. You should be able to open up the next section. That's okay. Just do as much as you can. Like I said, if you get anything for question 6, it'll be bonus marks over and above the 100%. Okay?
And then while we're here, I have a question about number 2 really quick. I had emailed you about it. It's
okay, let's have a look at problem 2. I'll have a look at my problem 2. Okay, so let me just make that a bit bigger so maybe we can all see it. Okay, so there is the circuit. How many KVL equations? Well,
I was just wondering how for the super KCL that you do for getting the current going through resistor 3 going into C. How do you find that as being in the negative direction?
It all depends, right? So let's just let me just copy that image and put it in here so I can doodle on it again, right? And let's see what we can do. Okay, so there's this is question 2. Where did my pen go? There it is. So this is Q2 and homework 4. Okay, so the issue with this one is because we've got 2 voltage sources. Let's just bring that down a bit so we can read it. So we have 2 KVLs. One is the freebie, right? That's at node A, because we know directly that VA equals V1. And one is the super node, and that one says that VB minus VC equals V2. Okay, and then your question is about the super KCL, right? And let's call it BC, right? It's the BC supernode. Now, the thing with mesh currents when you're doing mesh analysis and device currents when you're doing nodal analysis is it's completely up to you which direction you choose to have the current flow, right? So the only one in this diagram where we're sort of forced to keep a particular direction is for R4, right? We've really got to have IR4 going that way because it's nice to keep the passive sign convention happening, right? Because we've already got V out defined and its polarities defined. So we've got to say that IR4 goes from right to left. And then it's completely up to us for all the others which direction we choose IR1, IR2, and IR3. I tend to try and choose all directions to flow into the node in question, but that's just me. I could just as easily randomly choose them, flip a coin, okay, this one's flowing in, this one's flowing out, this one's flowing in, this one's flowing in. It really doesn't matter. So let's do that. Let's make that one flow in, that one flow out, and that one flow in. Right, so that's IR1, that's IR2, that's IR3. Okay, so then for this particular node, well, the super KCL equation is IR1 is flowing in, so we add it. IR2 is flowing out, so we subtract it. IR3 is flowing in, so we add it. And IR4 is flowing out. Okay, so there's our current KCL equation. Now we've got to change all of those device currents to being in terms of our unknowns, VA, VB, and VC. Right, so IR1 is just going to be VA minus VB on R1. IR2 is just going to be VB on R2. IR3 is going to be 0 minus VC on R3. And then IR4 is going to be VC minus VA on R4. And then that equals 0.
Okay, I got it. I didn't do the 0 minus VC over R3. I was trying to do, like I didn't have the 0 there, so I didn't have a negative and was doing positive there the whole time.
Okay, so, and like I said, we could have defined IR3 going this way, right? We could have defined it going the other way. In that case, this term would be flowing out of the supernode, so it would be minus IR3, right? And that would then be still be minus VC on R3. It all depends on, it still gives the same equation. It's just which direction and what that means in terms of whether it's 0 minus VC or VC minus 0, how you get the current from the voltages. Okay. Does anybody have any other questions about the nodal homework assignment? Sorry.
I'm all set.
Okay, very good. So I've forgotten what else we were going to talk about. We were going to talk about Lab 6, superposition. I have a slight problem in that where I am now is out of cell phone reception. So I can't actually access my Blackboard from here because I've got two-factor authentication turned on and I need to be able to receive a text message, and I can't. So let me just see if I can grab the Superposition Lab from my Dropbox. Just bear with me for a little bit. There we go, Lab 6 is Superposition. And can I download that?
Hey, Professor.
Yeah, what's up?
This is Jonathan. So the lab and the homework for is due tonight, right?
That is correct, yes.
Okay, awesome. Thank
No worries. So there is the lab. Let's see if we can insert it in here so I can play with it. Print out. Apologies for not being quite as well organized as I usually am. Okay. Okay, so we have a reasonably simple circuit, right? It's got 3 resistors, it's got a voltage source which is upside down, and it's got a current source. And the aim is to apply superposition. Remember what superposition is? That means that any independent source, voltage or current, will have the same effect on the circuit regardless of whether the other independent sources are in the circuit or not. So what that means is we can throw out all of the other independent sources and just keep one independent source at a time, analyze the circuit for that one independent source, and for every value, voltage or current, that we get, we can just sum up all of the solutions for replacing each independent source in turn, and the overall answer is just the sum of each of those independent solutions. So let's see if we can draw this. Right, so the first one on the left-hand side, the aim is to keep the voltage source, right? So if we keep the voltage source and we replace, remember, we replace all the other independent sources with their ideals. So the independent source is that we're replacing first up is the current source, and if we do that, we just replace it with an open circuit, because remember, the ideal for a current source is to set the current to 0. If we set the current to 0, that means we've effectively got an open circuit. So because of that, no current is going to flow in either of the highlighted branches. So the only thing we're interested in is Vs, R1 and R2, right? And okay. Similarly, when we replace Vs with its ideal, because it's a voltage source, we set the voltage of Vs to 0. That effectively means there's no voltage drop from one side of the source to the other. So that means it's the same node. Remember, a node is an area of constant voltage. So that means we replace the voltage source with a wire. So this is what we get. Right, we've got IS, R1, R2, and R3. Okay, so they're the two circuits we have to analyze. And I'll just check the numbers. So 1200, 270, and 560. So let me just put that up there and I'll draw them on here. So R1 is 1200 ohms. R2 is 270 ohms. R3 is 560 ohms. Vs is 10 volts. And IS is 5 milliamps, I think. Yeah, 5 milliamps. Okay. So then the aim is to figure out what the voltage drop across R1, R2 and R3 is, and also what the current through R1, R2 and R3 is. So for the first circuit, R3, which I didn't draw on, but it's this one up here, R3 has 0 volts and 0 amps. Right? There's nothing flowing through it. Because there's nothing flowing through it, Ohm's law still applies. V equals IR, V equals 0 times R, V equals 0. So then the question is, what's the total current? Well, one thing you can see is that there should be the same current through R1 as there is through R2. And the current's going to be 10 volts divided by, so let's call it I total, it's going to be 10 volts divided by R1 plus R2, because R1 and R2 are in series in the left-hand circuit. So it's going to be 1200 plus 270, which is 10 on 1470, and I'll have to use a calculator of some description to get that. So 10 on 1470, just use Google, and what's that? That's 6.803. 6.803 milliamps. So both of these currents are both the same. Let me go back to there. Both these currents are the same. They have to be. There's nowhere else for the current to flow. The voltages are going to be different. One of them is going to be 1200 times 6.803 and the other one's going to be 270 times 6.803. So let's see what those numbers are. So let's do times 1200. right? So that's 8.163 times R1 is 1200, I think. Yeah, so 8.163. And then R2 is going to be the current times 270, so it's 1.837. And just as a quick check, those two numbers, VR1 and VR2, should sum up to 10 volts, right? Now, I think I've done something wrong. Anybody got any ideas what I've done wrong?
Do you have the units written incorrectly?
No, I think my units are correct. It's got more to do with the sign I'm using, right? So,
Oh yes.
notice the voltage source here. I've actually got the current flowing the wrong way. If I've got the current flowing as if the positive was on the top and the negative. So really, the way this is drawn is the voltage being applied is minus 10 volts. So really, I probably should write both of those voltages as negative.
It's going to be 80.
Okay. So that's the first piece. So then we've got to look at the next piece, and the next piece, the second circuit, just has the current source, and we've sort of got a freebie on the current source, right? Because we know that the current through R3 has to be 5 milliamps. And that sort of makes sense. But then we've got 5 milliamps, so 0.005, and then the voltage drop is going to be IR, so it's 2.8 volts. Okay, so that's the first piece for R3. And then we have a current divider, right? So for the current divider, and I'm going to do the following. Because I had IR1 flowing that way, I'm going to make sure it's still flowing the same way. Right, so at the node A, right, I can write a KCL equation which says that IR1 minus IR2 plus IS equals 0, right? Because IS is flowing into node A. Only the current in R2 is flowing out. Now, I can find a relationship between, well, R1 and R2 are just forming a current divider, right? So I can say that IR2 is just equal to the resistance in the other branch, which is R1, divided by R1 plus R2 times IS. Let's just move that up a little bit maybe. There we go. So R1 is 1200 divided by 1200, and R2 is 270 times 5 milliamps. And let's see what that gives us. So that's 1200 divided by 1200 plus 270 times 5 milliamps. 4.08. And then I should be able to say, use the KCL equation. So IR1 equals IR2 minus IS. So IR1 so that's going to be 4.08 minus 5, which is minus 0.92. milliamps. And then I just need to multiply both of those by their respective resistances to get the voltage drop. So R2 is 270. So there's my current through R2, and that should, well, I had to multiply by 10 to the minus 3 because the number I had there was milliamps, right? So that's 1.102. And then the other one is 0.98 by 10 to the minus 3 times 0.92, sorry, by 10 to the minus 3 times 1200, which is R1, and it's 1.104. Now that's kind of interesting, right? Let's have a look at the circuit again. And really, where's the circuit? There's the circuit. Notice that R1 and R2 are both connected between the same two nodes. So the voltage across R1 should equal the voltage across R2. And okay, it's not quite equal. It's differing in the fourth significant figure because I didn't use enough significant figures in my current values. But it is showing up as being as VR1 equaling VR2. Okay. And then it's just a matter of ploughing ahead with all of that because the rest of the lab is basically asking you to solve the full circuit using mesh analysis or nodal analysis. I think it's mesh analysis might be good. And then construct the circuit in LT-SPICE. And then construct each of the smaller circuits in LT-SPICE and validate all the values for V1, V2, I1 and I2. Sum them and then look at what LT-SPICE tells you to do for the full circuit. And everything should add up, right? The sum of all of the entries in both of those tables, right, should give you how the full circuit works. And the LT-SPICE and mesh analysis should give you all of the same answers as summing these two tables, the entries in each of these two tables. And that's the power of superposition, right? It lets you analyze each circuit separately, or the effect of each independent source separately, and then combine those effects into the overall solution for the values. Any question about the lab? Okay.
I have a quick question, Professor.
Yep. Go for it, Jonathan.
Now, do you want us to put like the drawing and the numbers and the formulas all in the Excel template?
Yes, please.
Okay.
I realize I probably should set up an Excel template a bit better, but yes, put all the numbers. It'll make it much easier for you to add up the numbers in Excel. You can just use the math functions in Excel to do all the calculations for you. So it should make things a little bit easier rather than writing it all out. Okay. Okay, I think that's about all I had for the stuff due tonight. I'll go through the other stuff, homework 5, 6 and lab 7 next week. Like I said, they're quote due unquote next week, but you'll be able to hand them in at any stage before July 26th. I do want to get on to the Thevenin and Norton video and talk a little bit about Thevenin and Norton. But before that, I'll do what I normally do and have a break of about 15 minutes. So let's do that now, unless there are any questions. Okay, so let's go with a 15-minute timer.
Professor?
Yeah, what's up?
I know this is off topic, but in homework 3, question, let me get the question. I believe it's question 3 when it asks for like the IR1, the IR2. Let me get myself together. Let me see. Yes, for problem number 1 on the mesh analysis, is it just looking for the formulas like the I1 minus I2 or the equals 0?
This is question 1?
Yeah, part 3.
Part 3? Well, it's looking for what the actual values are for I1, I2, and I3.
All the value, okay.
Okay. Yours will
Okay,
be yours will be
right,
different because you have different different resistances and different voltages. Okay,
Yes.
so let's leave it there, and I'll be back in about 15 minutes. Okay. Everybody's deserted me except Van. Okay, so all I was intending to look at next is the Thevenin and Norton material that you should have available already. So unless, Van, you have a question, let's roll the video. So this is topic 9, which is Thevenin's theorem and Norton's theorem for CET236, Introductory Circuit Analysis. So this schedule for the summer of 2019, I've rejigged a little bit, but I'll talk to you about that directly. And so now we should have, after today's topic, we should have finished everything on the left-hand side. So you should understand everything that happens in that list. We'll continue next topic going down the right-hand side, but you should, after today's video, know what you need to know for all the topics on the left-hand side. So what's Thevenin's theorem? Thevenin's theorem says that if you have a circuit made up of sources and resistances, and that circuit is feeding a load resistance, then it's possible to replace that circuit driving the load with a much simpler circuit that just consists of a voltage source and a resistor, and that's it. And that voltage source plus series resistor is called the Thevenin equivalent of the original circuit. Right, and that's what this diagram is showing. The load resistance is external to the circuit, so that's the thing we're trying to drive with our fixed circuit, and we can convert our fixed circuit into a Thevenin equivalent. Similarly, Norton's theorem allows you to do the same thing, except rather than having a voltage source and a series resistor, now we can have a current source and a parallel resistor. Okay, so IN and RN, but it has exactly the same idea. You can replace a complex fixed circuit with a simpler Norton equivalent circuit. So there's three techniques I'm going to talk about quickly to figure out what the Thevenin or the Norton equivalent is, and some of them have a little bit of limitations, and the final one has no limitations. So the first one is equivalent resistance, and this limitation is that it can't have any dependent supplies. So the step one is to remove the load if it's not already removed. Replace all the independent supplies, because there are no dependent supplies in this if we're going to use this technique. Replace them with their ideal resistances, and remember their ideal resistances. For a voltage source, it's a wire, and for a current source, it's an open circuit. We set the voltage to 0, or we set the current to 0. And then you just find the equivalent resistance between the nodes where the load was connected, and that's going to give you the Thevenin resistance. So here's a simple example. If we remove the load here, we've got, and we've replaced the voltage supply with its equivalent resistance, which is a wire. And now we've got R3 in series with R1 in parallel with R2. And R1 in parallel with R2 looks like it gives us 2 ohms. In series with R3, this is an additional 5 ohms, giving us a total of 7 ohms. Okay, so that's how we find the Thevenin resistance. Now, one thing I haven't said yet is, how do you get the Norton resistance? Well, the Norton resistance value is exactly the same as the Thevenin resistance value. Okay, so we've found the Thevenin resistance here, but it's also the Norton resistance. Second technique is called the open circuit voltage or short circuit current technique. And this technique requires that we must have at least one independent supply. We can't have a circuit made up completely of dependent supplies. So step one, as with all of these, is to remove the load. Then we find the open circuit voltage between the nodes where the load was connected. So we take the load away and we figure out what the voltage there is without the load connected. Then we place a short across where the load was connected, and we figure out what that current is through the short, and it's called the short circuit current. And then the Thevenin resistance is the open circuit voltage divided by the short circuit current. And I think you should be able to see here, right? We've got, if we take away the load, then the open circuit voltage is just going to be given by the voltage at this point here, because if this is open circuit, if RL doesn't exist, then there's no current flowing through R3, so we're just interested in the voltage here. This is just a simple voltage divider, so it's going to be 6 divided by 3 plus 6 times 9. So that's going to be 6 on 9, right? So that's... So that, just a correction, that should have been 6 divided by 3 plus 6 times 12, right? Because the voltage source is a 12-volt supply.
2/3 of 12, which is 8 volts. So that's the open circuit voltage.
What? Hello?
Right, then we can...
Sorry, what's that?
replace the load with a short circuit and figure out what that current is. Right, and now we need to do probably a mesh analysis to figure out what the current is, or we could just do a series of voltage dividers.
Discord is being weird.
What's wrong? Hello, what's wrong?
And then a current divider approach to find out what the short circuit current is. The third technique you can use is the apply a voltage source. And here we remove the load again, as with all these techniques.
Can you hear me?
Yes, I can hear you. I can hear you. Please mute yourself. So let's...
there we go. Hello?
I can hear you. So
okay,
we're just watching the video. We're just watching the video at the moment. Yeah, what's the question?
I just saw your email. I reached out earlier Friday about booking the midterm because there wasn't slots. Were you able to open up slots?
That has already been opened up. You should. When I sent that email earlier, the slots were already open. They are open on the 20th, 21st, 22nd, and 23rd, I believe.
Okay, perfect. I'm gonna book it for the 23rd then.
Okay.
All right, thank you so much.
No worries.
We replace all the independent supplies with their ideal resistances. We place a new voltage supply between the nodes where the load was connected. You can pick this voltage. You can have any number, whatever it takes, 100, 2, pi, 3, whatever you want. And then you calculate the current through this new supply as it's connected to the circuit. And then the Thevenin resistance is that new voltage divided by the current that you calculated. Okay, so here's a look at starting the analysis of that. Right, we replace Vs with its ideal, which is, because it's a voltage supply, just a wire. Then we put a voltage source. In this case, I've chosen 42 volts as the voltage source. And now we want to calculate really what I2 is. But to do that, we need to do the mesh analysis to figure out I1 and I2. And in the next video, I'll do this analysis. Okay, so let's do this example of...
So any questions so far about Thevenin and Norton equivalent circuits?
Hold on 1 second. No.
Okay, well, let's have a look at the apply voltage technique.
Applying a voltage. Okay, so we're going to analyze it using mesh analysis. And the first one, let's look at I1. So this one down here, let's just do that in red. Right, so we have, for the I1 loop, we have 3I1, because remember we've got to have our positive and minus signs this way around. We've got this guy going this way, so that's the positive signs. 3I1 plus I1 6 times, and then it's I1 minus I2. For the I1 mesh, I2 is going in the opposite direction of I1, so it has to be negated. There's no voltage supply, so that's a 0. So that means we get 9I1 minus 6I2 equals 0. So then let's have a look at the I2 mesh, and the I2 mesh is going around like that, so we have a plus there, a minus there, a plus there, and a minus there. So for the I2 mesh, we have minus 42 volts because we're going into the negative side of the V new supply, plus 5 times I2 because we're going into the positive side of the 5 ohm resistor, and then plus 6 times I2 minus I1, and that equals 0. Okay, so let's rewrite that a bit, and we get that minus 5I1 plus 11I2 equals 42.
And just a correction, that should be minus 6I1, right? The 6 is out the front of I2 minus I1, so it should be minus 6I1 plus 11I2 equals 42.
Let's draw that properly. So that equals 42. Okay, so then we can go up here and, well, let's do it down here. We can write that out as 9 Now I think I got that wrong. Let me just have a look at that. What did I get wrong? Right, I got that this should be minus 6I1. Okay, I still get 5 plus 6 is 11I2. So that means I get 9 and minus 6 and 11 times I1 I2, and that equals, in the first instance it equals 0, in the second instance it equals 42. So that's what I need to plug into my calculator. Let's see if I can, I've still got my calculator going. I do have a calculator going. So let's see if I can remember how to do that. So second matrix, and I want to edit A is a 2 by 2 matrix. 2 is right, 2 is right. Now instead of that we've got 9 and then minus 6 and then minus 6 and 11. Okay, and then I'll go with B. So second matrix, edit, edit B, and for B I need to have 0 and 42. Okay, And then I'm going to second matrix A inverse B. No, I didn't want to do that. Let's
I always forget that.
let's clear that, and we just quit out of that. So let's just go back up and see if we can reproduce that, redo that. Okay, and see what that gives us. Right, so we get a 4 and a 6 for our I1 and I2. And that means that I2 is 6 amps. And that's our short circuit current.
So the piece that I didn't quite say then is that the voltage we applied is 42 volts. The current we got for I2, the short circuit current, was 6 amps. So the Thevenin resistance is 42 divided by 6, V nu divided by I nu, or I2. So the Thevenin equivalent for that circuit is the same as we got for the other two approaches, which is 7 ohms. Let me just quickly have a look at the slides for that topic. Right, that's Thevenin's theorem. Remember that the Norton resistance is equal to the Thevenin resistance. And the tricky bit is these three techniques only give you the Thevenin resistance. They don't give you, just grab, they don't give you the Thevenin voltage. Any ideas how to get the Thevenin voltage? Well, the Thevenin voltage, right, if you think about the circuit we've got when we're talking about a Thevenin equivalent, right, we've got VTH and RTH, and that's it. So if we measure the open circuit voltage, then that is nothing more than the Thevenin equivalent voltage. And then you could also, if you had a Norton equivalent circuit, right, you could put a short circuit here, and let me just move that up a bit. You could put a short circuit across the outputs of the Norton equivalent circuit, and that gives you the short circuit current, which will be the Norton current. And the nice thing about Thevenin equivalents and Norton equivalents is that VTH equals IN RTH. Right? So Ohm's law applies. So once you've got two of the three, once you've got the Thevenin voltage and the Thevenin resistance, you can calculate directly what the Norton current is. Similarly, once you've got the Norton current and the Norton resistance, for a start, the Norton resistance is also the Thevenin resistance, but you can then calculate directly what the Thevenin voltage is. Okay. Unless anybody has any questions, that is about all I intend to go through this evening. We'll be back at the usual channel, my office rather than my vacation bedroom next week. Okay. So if there are no other questions, I'll leave it there for this evening. Thank you very much for your attendance.